the first one, and then in the second one, we went over the rules for the conjunction operator. Here we'll go over the rules for the arrow operator. The arrow operator will get a little bit more complex when we do the arrow introduction rule, but the arrow elimination rule is fairly simple and goes along with the intuitive meaning of what the arrow means. So here's the statement of the rule in a picture. If you have phi arrows psi on a line, and on another line you have phi, then you can unlock psi and write psi by itself on a new line, of course indicating which rule you've used. You've used the arrow elimination rule on lines 1 and 2. Notice that you need 2 lines for the arrow elimination rule because you need to show which line you had phi and psi and which line you had phi. Here's an example of that. P arrows Q and P arrows R is our starting assumption. We also have P as a starting assumption. Well, we can't get to R or Q yet. We can't unlock those yet because those are locked in with this conjunction operator. So again, always look at what the main connective is. You need to break it down piece by piece with the main connective. So in order to say we want to unlock Q and R, first we need to unlock these 2 conjuncts. So we use the conjunction elimination on line 1 to get P arrows Q, and similarly we use conjunction elimination to get P arrows R. Now that we have P and then we have these 2 arrow statements, we can use our arrow elimination rule to unlock Q as we've done on line 5. Here we have an arrow elimination rule applied to lines 2 and 3. And then we can unlock R through our arrow elimination rule on lines 2 and 4. And we finish out this particular proof with combining Q and R on a new line with the conjunction introduction on lines 5 and 6. So again, this is fairly intuitive. It's just sort of what the arrow means. Say we have a statement like, if LeBron is injured, then the Lakers will lose. Well, if it happens that LeBron gets injured, then you conclude that the Lakers will lose. The rule for arrow introduction is a bit more complicated, but again, it goes with the intuitive idea of what the arrow means. But let's reframe that idea for a second. We're dealing with assumptions and deriving things from assumptions when we do proofs. So let's reframe the arrow in terms of assumptions. We can now read P arrows Q as assuming P, well then Q follows. So for example, if LeBron is injured, then the Lakers will lose. We all know that that would be translated to P arrows Q. Now let's think about that as, look, assuming LeBron is injured, the Lakers will lose. So if you have some sportscasters saying, hey, what do you think would happen if LeBron is injured? And you say, well, assuming LeBron is injured, I think the Lakers will lose. That's the sort of thing that the arrow statement is communicating. Assume something just to show that something else follows from it. This is why many ancient and medieval logicians called the arrow statement a hypothetical statement. So that leads to the basic idea of how we introduce the arrow into a proof. To introduce the arrow, you start with an assumption of phi and show that assuming phi leads to psi. If you've done that, then you can write phi arrows psi with the arrow by appealing to the arrow introduction rule. So that's how the arrow introduction works. Here it is in a picture. Again, suppose we have some unspecified first line of the proof here, and you're trying to get to this arrow statement. Well, what you need to do is assume phi, and then do a bunch of stuff in between. Who knows what you've done in between? And if you can get psi from this assumption, then you can then say, well, assuming phi, psi will follow, and that's just what the arrow means. And of course, always tracking how we derived that line, in this case using the arrow introduction rule. So that's all very abstract. Let's go through some concrete examples here. So suppose we're given the premise P arrows Q and R, and we're told to prove that P arrows R and Q follows from that. All we've done here is switch the order of the conjunction, and we know that that's going to follow because this doesn't change the meaning. Switching the order of the conjuncts doesn't change the meaning of an and statement. So how do we do this? Well, like with any proof, we start by listing our premise as an assumption, and we're going to show what follows from those assumptions. But now we need to introduce a new way of introducing new assumptions. So notice that we're going to introduce a new assumption here that is not one of the premises. We're going to assume P and mark it as an assumption. So just like when you're talking about LeBron James and saying, assuming LeBron James is injured, I think the Lakers will lose, you're not actually saying LeBron James is injured. You're just saying, if he were, then I would derive that the Lakers are going to lose. And that's what we're doing here. Because we're trying to prove an arrow statement, we need to show that if P was true, then R and Q would come about. So this is how we'll do that on the proof. We'll introduce P. Well, since we have P, we can now use arrow elimination to unlock Q and R. So we write Q and R on a new line and track how we did that with our arrow elimination rule. Now, because of our elimination of conjunction rule, we can apply that to line 3 and get Q by itself. We can do that again to get R by itself. And now we can conjoin Q and R to get R and Q. Again, with a conjunction, it doesn't matter. Notice that Q came first on line 4, R came second on line 5, but that doesn't matter. We can conjoin them in either order we want. So what we've done is kind of unlock Q and R from their logical connectives and then reorder them, and that's perfectly okay to do. Now, this is the important part. Because we simply assumed P, and it wasn't one of our premises, we need to indicate that, look, we assumed P, and then we showed what followed from it. But all of this stuff, 3, 4, and 5 here, we don't know whether that's true because we don't really know whether P is true. We didn't have license to assert P without qualification. We just wanted to assume P was true and see what followed from it. Now we're going to discharge that assumption and say we're not appealing to that assumption any longer after line 6. And that's what this dotted box here means. Namely that now I'm done with everything in this box. I'm never going to appeal to it again. What that allows us to do is then say, see, what I've shown you in the boxed area is that P will lead to R and Q. Now, I'm not saying P is true. I'm just saying that if P, then R and Q, and I've indicated that by the dotted boxes here. And of course, I've gotten that line 7 by appealing to the arrow introduction rule. And then what lines did I use to introduce? Well, I used all of the lines in the box, lines 2 through 6, all of these in the box. Okay, let's go over a couple more examples of arrow introduction. So again, suppose we have the premise P arrows Q, and we want to derive or show that this implies P arrows P and Q. Well, just like with any other proof, we start by listing our premise as an assumption. And because in this case, what we want to end up with is an arrow statement, again, we need to list a new assumption, which is going to be the antecedent of the arrow statement. So just assume the antecedent of the arrow statement. Now we need to show that P and Q will follow from that assumption. So we go to work. Of course, we can't do anything with line 2 because it's just a standalone proposition. We can do something with line 1 here, though. We have P, so we can unlock Q using our arrow elimination on lines 1 and 2. Well, now that we have P and Q here, we can conjoin them with the conjunction introduction. We have P and Q. Now we've drawn our box. We're done. We're done showing what follows from assuming P. Now the box is indicating that we're getting rid of that assumption. We're never going to appeal to it again. And we can use our arrow introduction rule to introduce this statement, P arrows, P and Q. And what this means is, look in the box. I've shown that if you assume P, not saying P is true, just saying hypothetically, if P were true, then P and Q would follow. And that's what this statement is doing there. So we've finished our proof for this particular example.